So today we're going to be starting differentials. Now, differentials is just a different way of writing down the notation, and we're going to see where that's going to play later on. We have a differential basically when we find the derivative or the change in y with respect to x. Each part of this is considered a differential. So I have a differential of y and a differential of x. Now we're going to rewrite this expression to isolate the differential of y. Like I said, later on, we're going to use this to contrast the differential, the expected change in y versus the actual change in y. So we're going to get a good start at that notation. This notation is also called Leibniz notation, fostered by Gottfried Leibniz. He was the guy who invented this type of notation, and so therefore we gave it his name with respect to him. So let's see how it's done. And now this should be mostly reviewed because doing the differential of this expression with respect to x isn't going to be too chaotic. I know the fact that my dy over dx, and yes, we are going to be writing it in this notation, is equal to the differential of this, which is going to be 6x, nothing going on there. In order to isolate the expected change in y, we're going to multiply both sides by dx, so I get dy is equal to 6x dx. And there we go. We have the differential of y isolated. Likewise, the next one, we can do the same thing. Now, with cosecant, one of the things that we have, we can either use the derivative rule for cosecant, or in this case, I've always liked to do cosecant's written as 1 over the sine of 2x. Or I could even rewrite that as 1 or y equals 1 times the sine of 2x raised to the negative first power. What this allows me to do is the derivative of sine is very straightforward. I know dy over dx is I'm going to treat this like a power, so negative 1 times that, so negative 1 times the sine of 2x, take away a power, so negative 2. Then I take the derivative of what's on the inside. So I'm going to take the derivative of, color coordinates just to make sure we keep track, of the sine of 2x. So the derivative of the sine of 2x is going to be the cosine of 2x. And then what I do is I take the derivative of what the cosine is of. So I'm going to take the derivative of 2x, which is going to be 2. So what I've got going on here is I have kind of a chain within a chain within a chain. I take the derivative of this using the power rule, derivative of that using trig rules, and then I take the derivative of what the angle is of using just normal power rules. Now I'm going to go ahead and clean this all up. So I'm going to say, okay, what's left up top is negative 1 times 2, so negative 2, and I still have the cosine of 2x. On the bottom, I'm going to have the sine of 2x squared, so I'm going to put sine squared of 2x, dy over dx. And now I'm going to multiply each side by the differential of x, so I'm going to be left with dy is equal to negative 2 cosine of 2x all over sine squared of 2x dx. Boom, Leibniz notation. There we go. So now that you've seen that it's really not any different than taking just the derivative with respect to x and then isolating the top of our differential expression, why don't you go ahead and try out number 5 on your own. Pause the video, see how well you do. Okay, now that you've had a shot at this, we notice that this is going to be not a chain rule, this is going to be a quotient rule. So I'm going to go ahead and set this up as my u is equal to x plus 1, which means u prime is equal to 1. V is equal to 2x minus 1, which means v prime is going to be equal to 2. I know that it's going to be low d high minus high d low all over low squared. So let's go ahead and pop that in. So I know, let's see, okay, so dy dx, we are taking the derivative at this point. Low d high, so this times 1 is 2x minus 1 minus high d low, so 2 times this, so 2 times x is 2x, 2 times 1 is 2, all over low squared, so 2x minus 1 squared. Now what I'm going to do is I'm going to clean this up a little bit and move the x over kind of at the same time. So I'm going to say dy is equal to, let's see, if I distribute that negative in, I have 2x minus 2x, which is going to cancel out. And then I have negative 1 minus 2, which is going to make it a negative 3. All over 2x minus 1 squared dx. There we go. We've isolated the differential of x in Leibniz notation. Awesome. So now why don't you try out number 7. Again, pause the video and pause when you're done and see all you did. Okay. So we notice that this is the natural log. So the natural log is of the square root, which means that's actually to the 1/2 power. I can go ahead and take that and move it out front. So y is equal to 1/2 the power of, or no, 1/2 of the natural log of 4 minus x squared. And this is going to make my derivative a lot easier to do because I don't need to chain rule this. I'm going to go ahead and take the derivative of the left. So I have the differential of y over the differential of x is equal to, let's see, 1/2. And I know the natural log is going to be 1 over this. So I'm just going to extend my fraction bar and say 4 minus x squared. And then I take the derivative of the inside, which is going to be a negative 2x. Awesome. So I'm going to go ahead and combine what I can, and then go ahead and pop that dx over there, the differential of x. So dy is equal to, let's see, 2 over 2 is going to cancel out, so I'm just left with a negative x all over, let's see, that's going to be an, well, those canceled out, so I just have 4 minus x squared dx. Differential of y isolated in Leibniz notation. Perfect. So now let's pop off to the last one. Now this one is an arc sine, so I know typically we don't do arc sines because we like to write them in versions of sines and cosines, but the arc sine has its own derivative in and of itself. And in case you don't have that on you, we know the derivative of arc sine, so I'm going to write this as d of arc sine of x, or how about of u, over dx, is going to be equal to, it's going to be 1 over the root of 1 minus u squared times u prime. So I'm just going to go ahead and put the u prime up top, which means you take 1 over the square root of 1 minus whatever this is of squared, and then you take the derivative of that and pop it in the top. So using that, we're going to rewrite this as a product rule. So I have my u and my v. So if u is x, u prime is 1. If v is the arc sine of x, v prime, now let's go ahead and look at this. So the derivative of this, the derivative of x, is going to be 1. And then I'm going to take the square root of 1 minus u squared. And my u in this case is going to be x squared. Perfect. And so with the product rule, it's just v du, or yeah, vu prime plus uv prime. So arc sine of x times that is going to be arc sine of x plus this. So I'm going to say plus x over root of 1 minus x squared. And then to isolate the differential of y, it's just going to be the differential of y is equal to arc sine of x plus x over root 1 minus x squared dx. Differential of y isolated in Leibniz notation, which is going to bring us to our next set of problems. So our next set of problems is going to involve comparing our differential of y to our delta y. And what we're going here is oftentimes we're going to use the differential or the derivative to estimate the behavior of what's going on. Now, oftentimes that isn't actually what's going on, but it's a good estimate because it saves us some time in measurement. So we're going to have the differential of y, which is our expected change, versus delta y, which is going to be our measured change. And we're going to assume a 0.1% acceptable tolerance. So we want to make sure that the difference is no more than 0.1%. So let's go ahead and let's take a look at the first question. And this is also going to give us a good chance to see what exactly is going on here. So if I have this graph right here, and I'm going to exaggerate a little bit of this. I'm going to say, okay, cool. I have this graph, it comes up, I've got some zeros at 0, and then it does that. Now, if I have a point at x equals 1, let's say it's right here, and I draw my tangent line, it's going to cut through it like that, and I want to find a differential of 0.1. Well, if I use my tangent line to estimate that, let's move out a total of, actually let's do this in blue, a total of 0.1 units out. I'm just going to make that as big as my numbers. I'm going to say, okay, what is the expected change? Now this expected change is going to be what we call the differential of y. If I move out, what am I expecting given this rate of change? What am I expecting it to be? Now the problem with that is the actual change is going to be this. So this is going to be delta y. And notice that the actual change is much bigger than the expected change. So we want to make sure that that difference is no more than 0.1%. So let's go ahead and figure out how we would do that. So for the first one, I'm going to figure out the actual delta y. And let's do this in, why not? Let's keep this in red. So let's figure out delta y, which means I need to figure out two things. I need to figure out what is the height at my point of 1. So I'm going to say y is equal to 0.5 at my point of 1. Let's plug this in black. Cubed. And so I get, let's see, 1 cubed is just 1, so y is equal to 0.5. I get that. Then I got to figure out what my height is 0.1 over. So I'm going to do it again and say 0.5 times not 1, but 1 over, so 0.1 cubed. Okay, and now for this one, I'm not going to be able to do this in my head. I'm going to need to go ahead and take out my buddy here. Okay, so I'm going to say 0.5 times 1.1 raised to the third power. And I get y is equal to 0.665 for an overall delta y of, let's see, 655. So 0.6655 minus my original 0.5. I have a delta y, which is 0.1655. And let's store that for later. Call my delta y, it's the first thing I found, so I'm going to store that in alpha A. Just in case we forget. That's my A. Okay, so that is the actual change. The graph went up by almost 0.2 of a unit. Let's find what the expected change would be had we used the derivative, so that instantaneous slope. And so let's take that graph, figure out differential of y, and I'm just going to find the derivative of this, which means that is going to be dy over dx equals, let's see, 0.5 times 3 is 1.5 x squared. And if I write this one more time, dy equals 1.5 x squared dx. Leibniz notation, so I've got this, and I'm going to plug this. Now I don't need to do this twice because I have both the x and the change in x. This is going to spit out my answer all in one go. So dy is equal to 1.5. So if I take my x squared, which was my original x, so I'm going to put that, why not, let's do that in 1, times the change in x, or the differential of x, which is going to be 0.1. So I can do both of these at the same time. And so my differential of y is going to be equal to, again, let's pause this and pop this in here. So I have 1.5 times 1 squared times 0.1. And let's see what I get. I get 0.15, so 0.15. I'm going to store this as my b. So store as b. Okay, so what I've got going on here is I want to find an acceptable tolerance no more than 0.1%. So we're going to calculate our acceptable tolerance by saying, hey, we know what our actual answer is going to be. And this is our given result, or so this would be given to us. So the formula for this is going to be the estimated minus the actual, ACT. I don't know what letter I just added in there. It's actual, so ACTUAL. Estimated minus actual over actual. I think I did it again. I don't know what's going on there. So I have estimated minus actual over actual, which means my estimated is going to be 0.15 minus my actual, which is going to be 0.1655 all over the actual. And so this will give us our percent difference of this. So that is going to be 0.1655. I think I put the decimal in the wrong spot right there. That should be a 0.1655. That should also be a 0.1655. And so let's see what the actual difference is. So I know that this is going to be my B. So I'm just going to go ahead and plug this in as alpha B minus alpha A. So 0.15 minus 0.1655, all divided by 0.1655, which is my A stored in here. So I have or not a tolerance rate, I have a change of, let's see, so negative 9.36%. I'm 9% off. Is that going to be acceptable of 0.1% acceptable tolerance? Well, the answer is no. This is not acceptable. And even though we were only 0.0155 off, we have almost a 9% error. We're underestimating by about 9% and not within our range. So now that you've seen one, why don't you go ahead and give number 13 a shot. Now this, I didn't give you the differential of 0.1. I gave you what the notation is going to look like. The change in x, which is equal to the differential in x, is equal to 0.01. So this change is going to be a lot smaller than what we previously did. Maybe this will be within tolerance. So go ahead and pause the video, unpause it when you're done, and see how well you did. Okay, so now that you've had a shot to try it out, let's see what this is going to do. Now I'm going to go ahead and draw a sketch just so I kind of see what's going on here. So I have this. I know this fourth power is going to be like a quadratic, but a little flatter. It's going to be something like that because it was shifted up by 1. I have a point over here on the left at -1, which means that I'm going to draw my tangent line like that. Probably should have drawn it a little farther over to give a good estimate. And what I'm going to be doing is I'm going to be moving over by 0.01. So 0.01, and I want to find the difference between this and this. So just to show you what's going on here, I'm going to redraw it right here. So I have a curve, and I have a point, which let's assume it does that. And there is my line. So yeah, here we go. So I've zoomed in a little bit. I want to find is the actual change within 0.1% of the expected change. So it looks like I'm going to drop a little bit. My expected change is a bigger amount. So what is the change between those two? So let's go ahead and get that set up for our first one, which is the actual change in y, which means I need to plug this into my formula twice. First, I'm going to plug in -1, then I'm going to add 0.01. So fourth plus 1. So let's plug in that -1. -1 to the fourth power is 1 plus 1, which is 2. And then I say, okay, I'm going to take that number and add 0.01, which means that it's going to be -0.99. Just a little bit over to the right. And now, I don't know about you, I can't do this by hand, so I'm gonna pop this out real quick and say, okay, what is, let's clear this, negative 0.99 raised to the 4th power plus 1. And I get that. So y is equal to 1.9605 for a total delta y of, take that, subtract my 2, I dropped by that amount. So negative 0.039, boom. And because this is a long decimal, I'm going to go ahead and store this as my first answer. Boom. Now that I find the actual drop in y, it didn't drop by very much, let's go ahead and find the differential of y, which means that I'm going to need to take my equation, y equals x to the 4th plus 1, and find the derivative. So dy over dx is equal to 4x cubed. The plus 1 disappears. If I rewrite this in Leibniz notation, I get dy is equal to 4x cubed dx. Go ahead and plug in my values. So the differential of y is equal to 4 times my actual x, which is negative 1, times the differential of x, which is 0.01. Kind of cut that off there. It's okay. Let's see what that is going to be. So I'm going to take 4 times negative 1 raised to the 3rd power times 0.01. And I get my differential of y is negative 0.04. So I actually dropped 0.039. I was expecting to drop 0.04, which is exactly what we expected. My tangent line was going to be a little bit below my actual. So is that within that 0.1% tolerance? So what we're going to do is we're going to take our estimated minus our actual all over our actual. So I estimated a drop of negative 0.04, and I actually dropped this thing, so I'm going to put negative 0.039, negative 0.039. Okay. And now, just to keep things easy, I know that that was saved as alpha A. I'm going to save this as alpha B. So all I need to do is say, okay, well, what is B minus A all divided by A? And I get a change of, let's see, 1.512% off. So I overestimated by about, or I guess you'd say I underestimated because I was under it, but I overestimated the change by about 1.5%. So this is also not acceptable. Pretty close, almost there, but I overestimated the difference by about 1.5%. So can't do that. But now that we've seen two numerically, let's take a look at one graphically, and let's compare. So what we've got going on here is we're going to use this graph to estimate the differential of y compared to the change in y at a change of 0.1 in my x and at a change of 1 in my x. So let's take a look at this. So for my first one, let's say I'm going to do my delta x is 0.1. So this is my a. So if I move over by 0.1, I can't actually physically see the difference there. So I'm going to say, let's see, delta y, the absolute value, so delta y minus the differential of y. I should have put that backwards because that's a little higher. But that's less than 0.1. I can't physically see that, so I'm going to go ahead and assume this is a good estimate. Not based off any actual numbers, but just based off of a visual look. It's pretty dang close. Now, if I do a difference of 1, so if I say for b right here, my delta x is equal to 1, That's from here to here. Oh, my graph doesn't even go that high. Let's go up there. So I have a change. Geez, it's almost 0.75 off. So let's actually put this the correct way. So I'm going to say my delta y, which is higher, minus my differential of y minus my delta y is roughly equal to 1, which in the scope of 3 and 4, that's a pretty big difference. So no, this is not a good estimate. So that's a really big gap there. And that's graphical. So there we go.